The first actual problem we're going to look at is one that we've already seen before, actually, back in Calculus 1. The scenario is this. I've got some function f. It has graph y equal f of x, which is the upper part of this region. I have some other function y equal g of x, where you have the bottom of the region. We're going to have x's that can be anything from some letter A to some letter B. And what we want to do is we want to calculate the area of the indicated region. Now, as I said, we already know how to solve this problem under certain situations. If both functions f and g take on only positive values on the interval which we're interested in, then if I were to calculate this area, the area under the f curve, it would just be the integral from a to b of f of x with respect to x. Likewise, presuming that g is positive, I can calculate this area, the area under the g curve from a to b, by looking at the integral from a to b with respect to x of g of x now, not f of x. And if I subtract the two areas, I get the area that I'm after. Because of the way that integrals work, of course, you can take this difference and write it as a single integral. If you have two numbers on a number line, then the distance along that number line is the bigger number minus the smaller number. If the number line is horizontal like it usually is, that's just going to mean the bigger number minus the smaller number. And by bigger, of course, I mean literally on the number line, the bigger number is the one that's to the right, and the smaller number is the one that's to the left. For example, if I want to know the distance between x equal 2 and x equals 6, I'll just subtract the two numbers. 6 minus 2 is 4, and that's going to be the distance. This is true even if one or the other of the numbers is not positive. If you look at -3 to 1, the bigger number is 1 because it's to the right, and the smaller one is -3. Bigger number minus smaller number comes up 4 again. And if you count 1, 2, 3, 4 units of distance, you see that that's right. So the two numbers do not both have to be positive in order for this to work out all right. In fact, they could both be negative and it'll still work out all right. My small number in this last bit is -5. The one that's further to the right, bigger one, is -1. And if you calculate the distance based on our previous idea, it should be the bigger number, -1, minus the smaller number, -5, which, after you get done simplifying it, comes up equal to 4 again. And as before, the distance is 1, 2, 3, 4 units of distance, as it should be. What I'm wanting to get across is I don't care if some of the numbers are negative. It doesn't make any difference. It's bigger number minus smaller number for the distance on the number line. This turns out to be true even if the number line is vertical, like a y-axis instead of an x-axis. Now, bigger means higher up, and smaller means lower down. So starting at 1 and traveling to 5 vertically, the big number is 5, the small number is 1, 5 minus 1 is 4, and you can count off the units of distance here, and you'll see that the distance actually is 4, like I'm saying it is. Start at vertical position 1 and go to -3, count the distance off. 1, 2, 3, 4 units of distance. The big number is 1, the small number is -3. 1 minus -3 works out to be 4. And just as we saw in the horizontal case, even if both numbers are negative, take the upper one minus the lower one, and you'll get the distance. I want to emphasize that distances are positive. Distances are not negative. And unless the 2 points you're talking about are the same point, distance is not 0. Besides that point, the area of a rectangle is the height times the width. So for instance, if you have a rectangle that's 3 units in one dimension and 2 units in the other dimension, you multiply the two numbers together, 3 times 2. The area of that rectangle would be 6 square units, whatever units you happen to be using. These are the only 2 facts we're going to need for the current discussion. What we're going to do to calculate the area that we're after is the same kind of setup that we talked about in what it meant to calculate a definite interval. I'm going to take the range of x values and chop it up into a bunch of smaller subintervals. I'm going to think about one of them. I'll think about one of them that I'll call subinterval number I. Its width, like before, is delta x number I. And the shape of the region that corresponds to that one subinterval is going to be some shape like this. What we're going to do is exactly what you think we're going to do. Within that subinterval, we're going to select a representative x number, which we'll call C number I, and I'm going to pretend that the height can't change much from the height at Ci. Now, when you're on the graph of a function, the function value is the y coordinate that goes with whatever x coordinate you're looking at. So this lower coordinate is going to be a g value. At any old x, it's g of x, but in particular, it's g of c, if I'm thinking about the representative point. So this coordinate's going to be g of c, and this is going to be y equal f of c. The area of that little chunk, since it resembles a rectangle, is going to be represented by height times width. The horizontal width is the difference between xi and xi minus 1. We called that delta x number I in the previous discussion. And the vertical height, we'll get that by thinking of the y-axis as a number line. It's the bigger y number minus the smaller y number. That would be f at Ci minus g at Ci. This quantity is approximately equal to the area between the two curves just on subinterval number I. And then again, we do what you think we're going to. To approximate the total area, we add up all of these contributions, and to get the exact area, we'll let all of the delta x's tend to 0. Taking the limit, we get the integral from a to b of f of x minus g of x with respect to x. This is the same formula that you got back in Calc 1, but unlike what happened there, I don't care if f and g are sometimes positive and sometimes negative. It is irrelevant to me. Also, I do care that the f is above the g. If that's not always true, we'll have to do something about that. For example, I want to think about the parabola, y equal x squared, and I want to think about the straight line, y equals 4 minus x, and I want to calculate the area between those two curves, starting at x equals 2 and ending at x equals 5. It's important that you draw the picture. So I drew the picture in between x equals 2 and x equals 5. Y equals x squared is always above y equals 4 minus x. So that's good. If I think of chopping this up into these little rectangles that we keep talking about, some of my rectangles will look like this. The horizontal is going to be one of the delta x numbers, and the vertical is going to be the big Y number minus the small y number, the upper Y number minus the lower Y number. If we want to be picky about it, we be all official on things, we will select a representative x value within subinterval number I. The upper y number is the square of the x number. So the upper y number is ci squared. The lower y number is the one that goes with the straight line in this case. This would be y equals 4 minus c. And the distance, the up and down vertical height of this rectangle is big Y minus small y. So the area of an individual rectangle is height times width. The total area is approximately the Riemann sum. To get the exact area, you have to take the limit as all of the delta xi's tend to 0 of the sum of these areas of rectangles that we've figured out. This is the definition of something. This is the integral from a to b of x squared minus the quantity 4 minus x dx. The smallest x value we're interested in is 2, so the a, the lower limit of integration, is going to be 2, and b, the upper limit of integration, will be 5. To finish this problem, you just have to do the integral from 2 to 5 of x squared minus 4 plus x with respect to x. I simplified that a little bit. This is a completely routine calculus 1 problem now, so I won't explicitly go through all the steps. When everything is said and done, the area between the two curves is 37.5 square units of area. A complicating factor. What if one of the graphs isn't always up above the other one? In the following example, that's the case. I want to find the area between y equals x squared and y equals 18 minus x squared, starting at x equal 2 and ending at x equal 4. I can't emphasize this enough. It's very important that you draw the picture so that you see what's going on. I used a calculator to draw this picture and then sketched it in by hand. These two graphs cross each other. Sometimes one of them is up above the other, and other times it's the other way around. I need to know where those graphs cross each other. Now, actually, since x goes from 2 up to 5, 4 maybe, this part is not important to me. I only care about the positive x coordinate of intersection. If you're at the intersection point, you have a certain x number, you put it into the two formulas, and you get the same y number back. So we're looking for places where 18 minus x squared equals x squared. And very quickly you find out that the positive x-coordinate of intersection is 3. So the x-coordinate of this point of intersection is 3. And unfortunately, that's right in the middle of the range of x values that we want to look at. So this is going to cause us a minor issue. We're wanting to find the area between the curves starting at x equal 2 and ending at x equal 4. Unfortunately, when the x value is between 2 and 3, 18 minus x squared is bigger than x squared. While on the other hand, if you're between x equal 3 and x equal 4, it's the other way around. X squared is higher up than 18 minus x squared. This isn't difficult to deal with. We just have to split the problem into 2 chunks. We'll find the area from 2 to 3, and then also we'll find the area from 3 to 4. And after we've done that, we'll add them together to get our total area. Here's the first part. Here's the second part. In the first part, our x numbers go from 2 to 3. The upstairs is 18 minus x squared. The downstairs is x squared. So thinking of one of our representative rectangles here, the area is the horizontal width times the vertical height, which is upstairs minus downstairs. 18 minus ci squared minus ci squared. On the other hand, between x equal 3 and x equal 4, y equal x squared is bigger than 18 minus x squared. Pick a representative c number within one of the subintervals that lies between x equal 3 and 4. The area is delta x as the horizontal width, and the up and down is the big y coordinate, ci squared, minus 18 minus ci squared, which is the small y coordinate. To get the area that goes with x being 2 to 3, I'll add these things up and take the limit. To get the area that goes with 3 to 4, I'll add these things up and take the limit. So I'll end up having to do 2 integrals here. Having said all that, the remaining calculations are perfectly routine calculus 1 problems. Simplify the integrand here to 18 minus 2x squared. An antiderivative for that is going to be 18x minus 2/3 x cubed. And then you would have to put x equals 2 and x equal 3 into that and subtract to get 5 1/3. I'm going to leave that as an exercise for the viewer because that's routine calculus 1 now. On the other hand, the second chunk has x's that go from 3 to 4. We're going to have to integrate from 3 to 4, x squared minus the quantity 18 minus x squared, which simplifies to 2x squared minus 18. Antiderivative is 2/3 x cubed minus 18x. Then put the 3 and the 4 in and subtract, and you get 6 2/3. A comment here, areas are not negative. If I were to make some mistakes here about which limits of integration I were going to put in, I might very well end up with a negative answer for one of them. That would tell me I've made a mistake someplace. Areas are not negative. The area of the first chunk plus the area of the second chunk adds up to be 12. The area between the 2 curves, starting at x equal 2 and ending at x equal 4, is 12 square units. I want to deliberately make some mistakes now. What if I somehow thought that I was supposed to integrate one of those two integrands all the way from 2 to 4? If I do the integral from 2 to 4 of 18 minus 2x squared with respect to x, after all is said and done, you end up with negative 1.3 repeating, which is obviously wrong because areas can't be negative. If you did something like that, that would be a clear indicator that you did something wrong. More tricky though, if I thought that I should integrate 2x squared minus 18 all the way from 2 to 4, the integral works out to be 1.3 repeating. If you didn't know any better, you would think that that's the total area, but it's wrong because sometimes the thing you're integrating is positive and sometimes it's negative. If you do either one of these two things, you've failed to take that fact into account, and therefore you get a wrong answer out of it. One of several things we're supposed to get out of this chapter is the idea that x isn't always the variable. So sometimes it's possible to slice one of these problems up in more than one way, and I want to look at that for this situation. We're going to look at y equals x squared, also known as x equals square root of y, and I want to find the indicated area. And in my first major video gaffe, I realized that on the previous page I had written some stuff down wrong, so sorry about that. Upper curve is actually y equals square root of x. X is going to go from 1 to 9, so the y starts off being 1 and can be as big as 3. Disregard what was on page 20 because it was wrong. I'm going to chop the range of x numbers from 1 to 9 up into a bunch of smaller ones. The horizontal width will be delta x number I as usual. The y-coordinate on the bottom is always 1. The y-coordinate upstairs is the square root of whatever the x-coordinate is. So the vertical height of this thing is upper minus lower. It's the square root of the CI number, and then you subtract 1 from that. The area of the rectangle is width times height. The Riemann sum is the sum of all of those areas of rectangles. And then to get the actual area involved, I have to take the limit of the sum, which in this case means I'm going to let all of the delta xi's tend to 0. This is literally the definition of an integral. This is the definition of the integral from 1 to 9 of square root of x minus 1 dx. An antiderivative for square root of x. Square root of x is x to the 1/2 power. So an antiderivative is x to the 3/2 power multiplied by the reciprocal of 3/2. The antiderivative of square root of x is 2/3 x to the 3/2 power. And then you have to subtract away x, which is antiderivative for 1. Evaluate that at x equal 1 and x equal 9, and you end up with 9.3 repeating. So this is the area of the region done in the way that we've been doing it previously. On the other hand, I could think of taking the range of y numbers, which goes from 1 to 3, and chopping it up into a bunch of smaller subintervals. I'll think about one of those as having vertical height delta y number I. So y is going to be the variable in the problem. I want to think about one of my rectangles. One of its dimensions is going to be delta y number I. The other dimension, what we were previously calling the height, is now horizontal. It's this distance. Now, the bigger of the x numbers is always going to be 9. The smaller of the x numbers, that's going to vary depending on what the y coordinate is. If y is square root of x, then x is y squared. This distance, the horizontal height, is 9 minus the x coordinate on the graph of y equals square root of x. And as I just said, the x coordinate would be y squared then. You might want to think about that kind of hard because we're using other variables than usual. So vertical height is delta yi. Horizontal height is bigger number, 9, minus smaller number, c number I squared, where ci is a y number that's in subinterval number I on the y-axis. The Riemann sums are going to be the sum of 9 minus ci squared delta y. When I take the limit, it's the delta y's that turn to 0 now, not the delta x's. Instead of replacing the ci's with x's in the limit, you replace them with y's instead, because that's the name of the variable in the problem now. So we're going to integrate from y equals 1 to y equals 3, because those are the y numbers that are relevant to our problem. The thing we're going to integrate is 9 minus y squared, and we're going to integrate that with respect to y. This looks kind of strange because we're so used to having x being the variable. Antiderivative, 9y minus y cubed over 3. It's the same game that you play ordinarily, except the name of the variable is different. You will evaluate that at y equal 1 and y equal 3 and subtract. And if you work the details out, you find out that the area is 9.3 repeating square units, just like it was the other way. And actually, looking at it, this integral is easier to do than the other one was because there's no fractional powers, there's no square root in it anymore. Sometimes one way will be easier than the other, and obviously, we always want to do things as easily as we can. Hopefully, this has been clear enough that you can easily see how you can calculate areas between curves. Number one, draw the picture so that you can see if the things cross or not. If they don't, then you do as we did early in the discussion. If they do, you have to split it up into 2 or more chunks. It's possible that using y as the variable might be easier than using x. That might be looked into. But in any case, you can reduce it down to ordinary definite integrals, then do the calculations and get the answer that you're after. Next up, we're going to take geometrical shapes in a plane and revolve them around a straight line so that we generate solid three-dimensional shapes. We want to be able to calculate the volumes of these things. We eventually will have 2 different ways of doing this. First, the disk Horseshoe method, and secondly, the shell method. We'll talk more about that in the next video.